Hey guys, so it should be Tuesday, March 12th for you. It is Thursday evening, extremely late for me. I recorded 3 videos and the mic was not turned on. So, this is not going to be exciting. At some point I'll turn totally monotone because that's what happens when I start to get tired making videos. So, here we go. Let's hope I can get through this. Let's see. So, starting off, we're doing a homework check number 1, you should be giving yourself 10 points for doing and then 5 points for checking. And tonight's homework is homework number 2. Tomorrow you'll have your quick quiz on 7.1, which is net change, and that'll be in partners. Alright, so if you are done your homework check and you don't have any questions, let Miss Semin continue the video. If not, tell her to press pause, and then Miss Semin, I'm going to show you. If you can insert the page after the current right here, that will let you insert pages in case they have questions from homework that you want to go over. All right, otherwise, if your homework check is done, let's move into the notes. All right, so 7.2 day 1. Here we go. We're finding the area bounded between the function y equals sine of x plus 3 and the x-axis. So I'm going to actually just shade that in first in our green. Let's see. So we're doing from 0 to 2 pi, and 2 pi is right here. And here is the area that we're going to try to find. And what you should notice is we can easily do that based off of the skills that we've already learned. We will be finding the area from 0 to 2 pi of the function sine of x plus 3 dx, and that this would actually get us the area bounded between there, because the net signed area, which is the integral, well, that happens to be the same as this green because the net signed area is all positive anyway. So that will work out perfect for us. Now, things I want to discuss before we really move on is, remember how this works in terms of RAM. This essentially gives us the height of our rectangles, and then this gives us our width of our rectangle. So if I drew a representative rectangle here, I want you to remember that that's what it looks like. The height is your function, your width is the dx, and then we would be summing a bunch of rectangles that are infinitely thin. And that's what gives us the Riemann sum, and that's what gives us actually the integral. We're doing a limit of all of those rectangles. So, moving on, I am going to bring that back a little bit later, so keep in mind that's where integrals come from, the fact that we're finding the area of a bunch of rectangles, okay? So, looking at example 2, we're going to use lines, and they're a little bit simpler to see, and it helps us simplify kind of the concept that we're going to look at. So, starting off, f of x is the blue line, g of x is 2, so that's here. And I want to find the area bounded between them from, and I'm actually going to do this in purple, from 2 until 6. So let's actually go in and shade that in. That's what I want to end up finding, okay, in purple. Well, obviously, we're going to end up using integrals to find that area. Let's start off with the integral from 2 to 6 of the function 3x plus 2 and see what that gives us. Well, 3x plus 2 would be the line. And it actually gives us the net signed area all the way to the x-axis. So that is a little bit too much. It's more than what we want. But that's a good starting place. Let's also look at the integral from 2 to 6 of g of x, which is 2. And that would be this little piece that's sitting right here. And I'm figuring most of you could figure out, well, if I gave you a big shape, and I say, well, I only want the area up here, but you happen to know the whole area, and you happen to know how big this piece is. Most of you can figure out you would take the whole area, which is an orange, and subtract out the pink area. Get that to go away, and then suddenly you have the leftover purple. So we're going to do exactly that. We are going to take this integral. Antiderivative would be 3x squared over 2 plus 2x, f of 6. 6 squared is 36 divided by 2 is 18. 18 times 3 is 54. plus 12, and that gives us 68. F of 2 would be 2 squared 4 divided by 2 is 2 times 3 is 6 plus 4 is 10. And therefore, the net signed area would be 68 minus 10. That gives us 58. So 58 represents the orange. That's this whole entire piece is 58. The pink antiderivative is 2x. F of 6 is 12. F of 2 would be 2 times 2 is just 4. And then obviously 12 minus 4 gives us 8. And so just by looking at those values, if I told you that this whole entire area here was 58, just like I have up there, and then this pink area down here was 8, you guys would easily tell me that the area left over is 50. Hopefully I did that correct. So I'm going to use that knowledge that we have. I actually want to talk a little bit about using representative rectangles. So let's go back to what I'm going to be finding is the area bounded right here. So here's my rectangle. And the rectangles are kind of nice because you don't have to worry about the trapezoidal shape. But if I asked you to find the area of that pink rectangle, but I tell you, oh, well, we can find the area of this whole orange rectangle, and I can even help you find the area of this blue rectangle, you would easily tell me, oh, subtract them to get the pink rectangle. That concept is exactly the same as what we're doing. Remember, the Riemann sum gets us to do a bunch of those rectangles, and that's how we're able to find the area bounded in between for the whole entire function and not just a little tiny piece or a sliver which represents that rectangle. So let's look at example 3. We're going to go from the same function down to -4. So I've changed the horizontal line to -4, but I'm still using the same bound, 2 until 6. So I'm going to actually try to use the same colors as before. Purple represents the whole area that I want. Orange represents the integral of f of x. Pink represents the integral of g of x. So let's go through. Integral from 2 to 6 of f of x. And what's nice is I'm using the same function, so we already know that answer, 58. And then in pink, let's look at g of x from 2 to 6 of -4. Now this we don't know. We can find the antiderivative. F of 6, which is -24, f of 2, which is -8, -24 minus -8 gives us -16. All right, so we got these two numbers. We got 58. We have -16. It should make sense why you get a negative because that rectangle happens to be below the x-axis. So in the very last problem, we actually took the areas and subtracted them. Most people, when they look at those two the rectangle and the trapezoid, they always tell me to add them. But look what happens if you add them. You would get the 58 and you'd be subtracting 16. So really, problem's no different than before. You still end up having to subtract. Because 58 minus -16, that is what's going to get us the total area. And that's 74 in this case. So I'm going to skip example 4 just to save a little time. And I'm going to look at the physical formula that I want you to remember. Kind of not exactly the way your book writes it, but it's going to be helpful. I want to go back to what we had before. Okay? Both of the functions we actually ended up subtracting, and what you did was you took the higher function and you subtracted away the integral of the lower function. Let's go back again. Higher function, lower function. And that's going to happen each time, anytime you try to find an area. So here is what I want you to write. If you want to find the area bounded between two curves, I want you to take the integral from a to b of the bigger function minus the smaller function. And let's talk about what does that really mean in terms of y values. How do you get a bigger y value? You would get a bigger y value by doing the top function, and you get a smaller y value by getting the bottom function. And that will work each time. And we do a dx because our rectangles, if you look at the way we drew them, go back, I'm going to erase a little bit. Look at the way my rectangle looks if I'm going from here down to that line. The rectangle itself has a top, and the rectangle itself has a bottom. So that's how I know it's a dx problem, okay? That probably doesn't make much sense to you guys, because you pretty much always do dx problems. So now I'm going to go into, what do we do to find the area between curves? Well, there's two types of problems you'll get. You'll get some that the graph is given, and that's going to be a lot easier. And you'll have some where the graph itself is not given. If the graph isn't given and it's easy to draw, do it. It makes it a lot easier to have the graph. But if you're not given or you're given functions that are just too difficult to graph, what you want to do is kind of mentally end up figuring out what the graph would look like. Now, this only works for when they tell you that the bounds are two functions. No axes, no extra lines, just two functions themselves. So they say, oh, find the area bounded between f of x and g of x. That's all they say. In that case, your first thing you're going to try to find is the intersection between the two functions. And how do we find intersections? We take the functions and make them equal to each other. I'm going to take a pause right now. Ms. Stedman, can you just make sure that everyone is awake and paying attention? Because I know that it is really boring to listen to the videos. So kind of give them a breather, let them stand up, shake it out, stretch their legs, jumping jacks, push-ups, I don't know, but whatever gets them to kind of be a little awake. All right, so if you are done kind of stretching and just breathing, let's get back. So, intersections. So let's try to make sense of this. There's a function f that does something like this. And let me make sure it's actually a function and not curving back like that. And then let's say there's a function g. So, and we say that the area we want just completely bounded between those two functions. Well, look at the intersections. They're going to tell you where you're going to start your integrals and where you're going to stop your integrals. That's why the intersections are going to be important. Now, second part you're going to do is once you find your intersections, you're going to make a kind of like a sign chart, but you will find an x value in each interval and identify the big and small functions. So in this case, you can say big or top and small, which is in this case bottom function. All right, so let's think about that. How would you do that? Well, here, let's call that A, let's call that B, let's call that C, and then we're going to find an x value right here. Okay, we're going to call that x value a new value. Let's call it D. And I take that D value and I put it into the f function, and then I put it also into the g function. And depending on the values, you'll easily be able to tell which one's bigger and which one's smaller. So why is that helpful? Well, let's think about that representative rectangle. The bigger function would be considered my top function, the smaller function would be considered my bottom function, and we know we could figure that out based on y values. That's why number 2 is going to be very important. Well, look at what happens though. Notice which function's on top. It's the blue function, which is f. But notice which function's on top now. It is the g function. And the intersections are the only times that the functions can switch top and bottom. There's no way for a function to switch its location in terms of above and below or bigger and smaller unless the functions intersect. And that's why that step 2 is so important. Step 3, you're going to put that into your integrals, which are the big function minus the small function, and in this case it's the dx problem, because dx problems have rectangles that have top and bottom. That's a dx rectangle. All right, so given those steps, let's do a problem. I gave you the graph only so that we could confirm what we're doing, but let's pretend the graphs are not given. They give you these two functions. I'm going to rewrite them right here. They give you function f which is 2 minus x squared, and they give you function g, which is negative x. So we're going to go through those same steps. The first thing is I got to find where they intersect. So take the functions, set them equal to each other. This is going to be a quadratic function, so I'm going to set the equation equal to 0. And then I'm going to factor. The factors would be negative 2 and positive 1. X is equal to 2, and x is equal to negative 1. So there are my intersections. Now, because they're telling me that the functions are completely bounded by those two, I know that from negative 1 to 2, there's going to be a top function and a bottom function, and because there's only one set of intersections, I won't have to worry about them switching. I'll have one integral only. So obviously the value I'm going to pick is 0. F of 0 is 2. G of 0 is 0. Therefore, f of 0 is my bigger value, which means that's got to be my top function. So step 3, do my integral. I'm going from negative 1 to 2, my top function being the f function, oopsie squared. My bottom function being the g function, negative x, dx. And then before you try to integrate, simplify, it makes it a little bit easier for you. So negative x squared, positive x, positive 2, and then dx. That way, it's a little bit easier to take your integral. All right? My assumption is you could do your antiderivative, you can do your f of 2, and you can do your f of negative 1 to subtract them to get your final answer. So go ahead and ask Ms. Seven to pause this if you have any questions. Obviously, throughout any lessons that I do from video, ask Ms. Seven to pause if you get stuck. All right. So now, this one can be a little tricky. This is one where they'd have to give you the graph, or you'd have to graph it yourself. And how do I know that? It's because they give us all these weird bounds. You get a line and you get a function, but on top of that, you get the x-axis. And whenever they give you x-axis or other horizontal vertical lines, you always want to draw out what they're giving. So there's the graph. Now, when you're given a graph, you then get to draw your representative rectangle. And what I do is I actually do a T and a B, and that way you'll kind of know which one's the top, which one's the bottom. What I want you to notice is what happens when I come over here and do that. Notice your top and bottom. The top is still the blue line, but the bottom has now switched from being the x-axis to now the red line. What that means, I'm going to have to do 2 integrals to do this problem. Anytime the top and bottom are different, you need 2 integrals. So we're going to do an integral from 0 to 2 of the top function being the blue, which is root of x, the bottom function being 0, plus the integral from 2 to 4, the top function still being the root of x, but now the bottom function has switched to the line x minus 2. And that's really, really important. Now that should look weird to you because you don't really need a bottom function when it's the x-axis. That is exactly the same thing as finding the net signed area. So it may look a little odd, but if you want to always use the top and bottom using the representative rectangle, it can help. And minus 0 just means you simplify that out anyway. All right, so remember to distribute your negative. That's a step that you're going to forget. Minus x plus 2 dx, and then obviously you would integrate the 2 separate functions by finding their antiderivative. All right? Number 3, taking a look at this problem, again, we're going to pretend like the graph is not there. So you would find the area bounded completely by 2 curves. That would be one where you don't even need the graph. I know I would find the intersection first by setting negative x squared plus 3x equal to positive 2x cubed minus x squared minus 5x. Since that's a polynomial, I'm going to set it equal to 0. X squared will cancel, and then I'll have minus 8x. I'm going to factor out the 2x, and I get x squared minus 4. If you guys could factor that out completely, you should realize that now you have 2x times x minus 2, and then x plus 2. So there's a total of 3 intersections. They are 0, positive 2, and negative 2. Step 2, number line, negative 2, 0, and 2. We're going to pick values in between. So here, I would obviously pick -1. And then here, I would do g of -1. So I think we called them f and g. So f of -1 would be -4. G of -1 would be -2 plus, wow, I'm having some trouble here. So -2 minus 1 plus 5. So we get +2. So now I know that g is my top function or my big function. Then in between here, I'm going to pick +1. F of 1 would be 2. And g of 1 would be 2 minus 1 minus 5. And that gives us -4. Huh. There's your top function. So they actually do switch locations. Top ends up being a different function the second time. And you can see that obviously in the graph that's here. The first time from 0, the first interval from -2 to 0, the top function is the red. But then from 0 to 2, top function is the blue. So they did switch. So my third part would be the two integrals, and I'll do them on two separate lines because I'm going to run out of room. First integral was from -2 to 0. The top function is my g of x, which you can see right here because it's boxed. G of x would be 2x cubed minus x squared minus 5x, and then minus my f of x, which is -x squared plus 3x dx. And then I would physically add the other integral, which I'll do in orange, which would go from 0 until +2, my f function being my top function, -x squared plus 3x, and then my bottom function being the 2x cubed minus x squared minus 5x dx. Very long problem, but you would go through and simplify. Don't forget to distribute your negative before integrating. All right? There's one last thing I need to show you, and that is integrating with respect to y. So there is a reason why I kept talking about these representative rectangles. We just did this problem, and our representative rectangle going this way showed us that we needed two integrals. Well, this same problem can be done with one integral. And how do I know that? Because we can actually integrate with respect to y, which we don't usually do. When we did our RAMs, they were all dx problems. So I want you to recognize that these rectangles are not familiar. We're used to doing vertical rectangles. So anytime you do a horizontal rectangle, it tells you horizontal rectangles are dy problems. Now, how do I know? The concept is pretty much the same. You're still going to look at bigger and smaller. Well, if you're looking at side by side, that would be the x-axis. Where are your bigger x values? Well, they're on the right side. And where are your smaller x values? They're on the left side. So that is how I label my dy rectangles. If you look here, I would do a right side and a left side. And the reason why this problem is nice to do as a dy, you'll notice that the right and left, the functions don't change. So there is an extra step. If you're doing a dy problem where your rectangles go side to side, right and left, there is one extra step. And we're going to put that in the beginning so we don't forget. Solve each equation for x. So you're going to solve the equation for x, which means your functions will be in terms of y. That's going to be really important. In terms of everything else, you're going to find your intersection still the same. X value in each interval. And this is where the big function will be considered the right function, and the small function is the left function. But big and small, your values, that's still what you're going to look for. You're going to look for the biggest x value and the smallest x value. And, oh, sorry, wow, made a little mistake there. You're actually going to substitute in y values. That's the difference. And when you do step 4, your integral from a to b will be of f of y minus g of y dy, given that f and g, f being the bigger and g being the smaller. So there's a slight difference, this being one of them. And then obviously step 1 is brand new. So we're going to do this actual problem using those steps over here. So, oh, I forgot I did that. So given this problem, you actually are going to do it as a dy problem. So we're going to follow the exact step. My first step is the fact that I need to switch my functions. Well, this is root of x, so I'm going to square both sides. And when you square both sides, you don't use a plus or minus. Okay? And then the other function, y equals x minus 2. I'm going to solve for x, and that gives me y plus 2. This here and this here are the functions I'm going to use to find my area. Step 2 would be setting them equal to each other to find my intersections. Now in this case, this will look somewhat similar. Okay? And we're going to factor. And we get that y is equal to 2 and negative 1. Well, negative 1 won't make sense because if you're talking about root of x, the root of x is always going to give you a positive value. That's one of the reasons. Second reason, the graph is only in the first quadrant, so no negative y values can make sense. Now looking at step 3, actually I should be able to fit it here. We're going to go from, in this case, we know we're going from 0 until a positive y value of 2. And I just need to make sure you remember, we're doing a dy value, problem. That means these are all y values. So I'm going from a y value of 0 until a y value of 2. That's what the y values represent. The other thing you want to understand, so they represent where your rectangles start and then where your rectangles would end. They would end at 2. In terms of picking a y value, I would pick 1. So when y equals 1, f of 1 would be the 1 squared. Where am I getting that from? I'm getting that from here. Okay? And then g of 1 would be 1 plus 2, which is 3. And again, I'm getting that from here, this function. So my f function, in case you're a little bit confused because it looks a little bit funny, I'm going to rewrite them right here. This is considered f of y, and this function is considered g of y. Okay? So, step 4, now I know that this is my bigger function, g. Then I know my integral goes from 0 to 2, and I'm going to do g of y, which is y plus 2, minus f of y, which is y squared, dy. Things to check. These all have to be y values. Sorry, I shouldn't say y values, the variable y. That's easier. And then this here and this here, those need to be physical y values, not x values. So they are going to be the values that you can look at going up and down here. All right? So that should pretty much be the last problem. I think there's a multiple choice question at the end here. And that multiple choice question you can do just by graphing. It actually ends up being a pretty simple question once you graph. I use this problem to talk about how to graph e to the 1/2 x. Well, that's very similar to e to the x, only it's a horizontal stretch. If you have no idea what the graph looks like, but you at least should know that this is what e to the x looks like, okay? Then choose values. Substitute in 0, you get 1. Substitute in 1, you get e to the 1/2. Substitute in, which is the same thing as square root of e. Substitute in 2, and you get e. These values are easy enough for you to graph, and you know it looks like this graph. Then I know that I can graph it. It's going to be enough. So x equal to 0 is this vertical line. X equal to 2 is a vertical line at 2. Y equal to 0 is this flat blue line, the x-axis. And then the curve is interesting. You're going from y 0, 1 to 2, comma e. So what's interesting about this is you could do this problem 2 different ways. You could do it using top and bottom. Or what could end up being just the same is, that's the same thing as just a plain old integral. So the 2 ways, if you do top and bottom, you would go from an x value of 0 to an x value of 2. I would be doing top function is e to the x over 2. Bottom function is 0. But that is exactly the same thing as you just finding the plain old integral of the function given. Okay? So at this point, if there's any time left, you can work on homework or ask Miss Stedman any questions or ask her to rewind to anything you need.